analysis of corrected thermodynamics of 3D black holes in AdS spacetime conformally in the background of massless scalar field. The outline of my talk will be about introduction of black hole and its thermodynamic system, then about 3D conformal black holes and its corrected thermodynamics parameters, and last will be about conclusion of my results I have found. Einstein's theory of general relativity has predicted the existence of black holes. So what is black holes? A black hole is a region of space-time where gravity is so strong that nothing, not even light, has enough energy to escape the event horizon of the black hole. And it is formed when the size of gravitating object becomes smaller than its gravitational radius, which is called Schwarzschild radius. And it is given as 2gm by cs square, where g is the Newtonian gravitational constant and m is the mass of the gravitational object. For example, let's talk about the familiar astronomical objects like Sun, which has a mass of about 20 to 10 to the power 30 kg, will become a black hole when its gravitational radius shrink to just about 3 kilometers. And for Earth, this Schwarzschild radius is less than 8.7 millimeter. And for Moon, it is just less than 0.1 millimeter. Now let's talk about black hole thermodynamics. There is a formal analogy between the laws of thermodynamic system and the black hole physics has been found. This was first proposed by Jacob Bekenstein, and later contributions were made by Stephen Hawking and others. For example, when a black hole observe a mass, say delta m, then its mass will increase to m plus delta m, and simultaneously its area will also increase. Since the horizon can be crossed in just one direction, area of black hole can only be increased and it will never decrease because nothing is coming out from the event horizon. This suggests an analogous with the entropy of a thermodynamic system. Later on, association of standard thermodynamics parameters were proposed for the black hole parameters. For example, temperature. This has been found that this is found to be analogous to the surface gravity of black holes, and entropy with the area of the horizon, and energy or internal energy with the mass of the black hole, and pressure with the angular velocity of the horizon, and volume of a thermodynamic system with the angular momentum of the black hole. Based on all this analogy, four law of black hole mechanics has been formulated and found to be analogous to the thermodynamic system. For example, zeroth law of the thermodynamics, which talks about the thermal equilibrium. It says that energy stops flowing at the thermal equilibrium. Similar analogy has been found in black hole, where surface gravity is considered to be the constant over the event horizon. First law of thermodynamics, which talks about the conservation of energy, says that in the thermodynamic system, energy is always conserved. Similar analogy has been found in black hole with the change in mass of the black hole system, which is found to be equal to the change in area, angular momentum, or the charge, and other parameters. That is, difference in mass are equal to the difference in area times the surface gravity with the additional work type terms in the black hole system. In second law of thermodynamics, which is about the entropy of the thermodynamic system, it says that in a closed system, entropy always tends to increase over time. It never decreases. Similar analogy has been found in the black holes, where the area of the event horizon never decreases. It keeps on increasing. In third law of thermodynamics, it says that it is impossible to reach the absolute zero temperature in a thermodynamic system. This analogy has been found in black hole physics, where surface gravity can not be made zero in a black hole system. Similarly, like black body radiation, Stephen had proposed the black hole also emits quanta that arises due to the creation of tight virtual pairs of particles, and tidal forces pull them apart, with one pair of these particles fall inside the black holes, and which is inaccessible to the outside world, and the other one flies away. This is known as black hole evaporation. The Hawking has proposed that the radiation temperature of the black hole is inversely proportional to its mass and is given by this relation. So, smaller black holes are larger emitter of Hawking radiation than the bigger ones. Once the black hole that do not gain energy or mass from the outside will keep heating up by emitting Hawking radiation, and its size keep on decreasing, and finally it evaporates completely on attaining thermal equilibrium with the surrounding. Now let's talk about the 3D conformal black holes. Black holes were first conjectured in 4D through the Einstein's general theory of relativity as the gravitational collapse of massive structure. But one cannot have 3D black hole solution as the Bell tensor and Ricci tensor vanishes in the absence of matter. But after the discovery of BTG black hole solution, several 3D black hole solutions have been explored. So here we have considered a 3D black holes conformally coupled with a massless scalar field for the study. For 3D conformal black holes, Einstein-Hilbert action has been Einstein-Hilbert action for the conformally coupled massless scalar field has been given by this relation, where R is the Ricci scalar and L is the cosmological constant length, and phi is the massless scalar field coupled with the Ricci scalar. The solution of the black holes in the symmetric metric function has been found to be equal to R plus B ka whole square into R minus 2B by RL square, where B is an integration constant found in the solution, which is related to the origin radius of the black holes and is equal to the half of the origin radius. Once we have the metric solution of the black holes, Hawking temperature can be found to be 1/4 pi of differentiation of metric function with the origin radius, and it is found to be equal to 9R plus by 16 pi L square, where R plus is the origin radius of the black holes. And using the Waltz formula, entropy at the equilibrium is found to be equal to pi R plus by 3. For the corrected thermodynamics of this system, thermal systems do not follow the second law of thermodynamics without incorporating the concept of entropy. On various occasions, it is confirmed that the maximum entropy of black holes requires correction. So for this, we have considered here a logarithmic correction to the entropy of the black holes, and is calculated from the relation S equal to S naught minus alpha ln S naught T square, where S naught is the uncorrected entropy of the black hole system, and alpha is the correction parameter, and Th is the Hawking temperature. And from the value of S naught and Th, it is found that the corrected entropy of the system is equal to pi r plus by 3 minus alpha ln 27 r cube by 256 pi l to the power 4. And its plot has been shown in the right side of the screen, and the corrected one is shown in the red line. And it is found that the corrected entropy is always positive and a decreasing function below the critical horizon radius. But above this point, it is always an increasing function. Hence, for the larger black holes, the corrected entropy does not have much significant effect on the thermodynamics of the black holes. But for the black hole system, for the smaller black hole system, it has a significant effect on the entropy of the system. Once we have the correction in the entropy of the black holes, various thermodynamics variables due to a small thermal fluctuation at the equilibrium has been studied, like the Helmholtz free energy, internal energy, its pressure, enthalpy, and Gibbs free energy. For the study of the stability of black holes, a specific heat has been studied. Once we have the entropy of the black hole system, volume of the thermodynamic volume of the black holes can be calculated from the 4 times of the integral of S naught dr, which is found to be 2/3 of pi r square. Now the Helmholtz free energy. Helmholtz free energy of the black holes can be calculated from the thermodynamic relation equal to the minus integral of S dt, where S is the corrected term entropy of the black holes and T.
Thank you. I think there is no time for any question. Anyone can ask question in the chat box or use discussion room. So I invite the next speaker, but not last. Please do not leave the room after this talk. We have a surprising talk.